beginning, hey, this is a parabola that we could solve for y squared instead, or sorry, solve for x. You could have seen it as a sideways parabola. At the end of it all, though, you need to be able to just come up with a picture, okay? So do we all agree we have a picture that's relatively good to work with? Do you all see the region bounded by the two? That one? No. That one? That one, right? Okay, so I hope it's pretty evident to you from our picture that this is the region that we're talking about. Now, we have a major problem. We have a major problem. What's our major problem? Yeah, so think about if I tried to draw a rectangle right now, okay? Just think about if I tried to draw a rectangle. If I drew my rectangle right here, would I have a very clear and distinct upward or top function? What's my top function here? This one. And my bottom function would be one of these root functions, right? One of those two over there, right? But then once I get over here, like remember this rectangle slides, doesn't it? So when I get over here, my top function and bottom function, well, my top function is different, isn't it? Yeah. My top function has switched from the blue one over to the red one. So I have like a new top function and a different bottom function. Agreed? Yeah. Now maybe we should take the time to just clearly state that this is the positive root of 12 minus 4x, and this one is the negative root of 12 minus 4x. So we still do have a top function that is different than the bottom function here. Agreed? If we do it this way, what do you think we're going to have to do? If we're going to stick with this way, what are we going to need to do? Split it up. We're going to need to know where these two hit, aren't we? Yeah. Because that will tell us where we're going to do one integral to take care of this one, right? And then a new integral to take care of this one. Does that make sense? Do you think we could do that? Sure. But there's a more efficient way. All right? There's a better way. There's a better way. And that's to completely change our perspective on the problem. All right? So I'd like to redraw the picture. I'm just going to say, from this, yeah, we could do it, right? Yeah. We could do it with two integrals. Right? And we would also have to find that point of intersection. Okay. Let me redraw. When we started this problem, I heard a couple of people say, okay, we have to solve for y, right? Yeah. And that's because anytime we've solved for y equals, let's say, go back to that one we had earlier, like that, then we could say that y is a function of x, right? If you can solve for y, then we're saying y is a function of x. But what happens if we take an equation and solve it for x? Then it becomes a function of y, doesn't it? So instead of solving for x, instead of solving for y on these, I'd like us to consider solving them for x instead. So let's take a look at this first one. This first one, it's already solved for x, isn't it? X equals y. But if I solve this for x, let's see what we would get. Right? That. Then divide by 4. No, that's not a 4. That's a 3. Then I get x is that, right? Y'all agree with that? Okay, now, if I go to look at my graph, it's the same picture, okay? I haven't changed what these look like. What I've changed is what they are functions of. So when I draw my diagonal in here, this is now x is y, right? Yeah. Instead of y is x, same thing, big deal. But this one that does this, sorry, it's really bad. Can you all see that this is a parabola that opens not down, But the negative means it opens to the left. Positive in front of the y squared would open it to the right. It's almost like this. Like everything you've known with parabolas, just tilt your head sideways, okay? So now you've got, it moved up 3, right? And it opens down. That's what this is saying, basically, right? Do y'all see it? Okay. Now, all we're doing right now is we're taking our entire mental perspective and seriously, we are rotating it 90 degrees and looking at it that way. So instead of drawing vertical rectangles, I'm now going to draw horizontal rectangles. So imagine I want this area in here, and now I'm going to draw a rectangle this way, and I'm going to start adding all those up. Okay? So let's talk about what this thing looks like. So I'm going to extend my y-axis down. Instead of coming over to the side this way, come down here, and I'm going to take a look at what this area of this thing would be. So how wide is this rectangle this way? dy, not dx, because you're moving the rectangle this way now, right? Yeah. So y is changing. So this is now dy, right? We still have a top function and a bottom, but we can't say top and bottom because top is here, bottom's here. We actually have a right function and a left function. So the right function would be the parabola guy, right? Yeah. And the left function would be the line guy, right? So what would this distance be? And remember, it's the difference in the y coordinates, not the x coordinates anymore, right? It's the difference in the y coordinates. But that's okay because we solved these for x, didn't we? Yeah. So what is the one on the right side? That's that one, right? That's that one. So shouldn't this be the 3 minus 1/4 y squared, right? That would be this distance. Then we take away this distance. So what's that distance? Y. Not x, but y. See how we switched everything from x's to y's? Did y'all see that? Are you sure? Yes. And we have, instead of top and bottom, we have right and we have left. Instead of top minus bottom, it's right minus left. Instead of dx, it's dy. Yeah? Sure. Do you notice that as we move our rectangle, the right function and left function never have to change? Remember in the previous, we said we could have done it, but we'd have to do 2 integrals. We'd have to find the point of intersection, yes? Here, we're never going to have a change from our right function to our left function. They're always the same ones. Now, we do have to still move the rectangle, don't we? And we need to move it. Yeah, okay, so let's start putting this together into our formula. We want to set up our integral. That's going to add all these guys up. And we're going to be doing the 3 minus 1/4 y squared minus y, right? That's dy. That's the area of one of these guys, right? And then the integral adds them up. But now we want to move the rectangle up and down, which means we are changing its y coordinate, aren't we? Not the x coordinate. The y coordinate's got to move. So where do we start our y coordinate out? Where does it start at? The intersection here, right? We need to figure out this y value, and we need to figure out this y value. So instead of going x, a and b, right? We're going to be going here and here. Now, we'll call this c and d when I'm going to put the formula up here in a second, just so we have it. But we're going to go from c to d instead of from a to b. All right, so how do we find those? Set them equal to each other, right? Just like we did before. But since they're both solved for x, although I erased it over here, this was x was equal to 3 minus 1/4 y squared. Since they're both solved for x, I set the x's equal to each other, and we get 3 minus 1/4 y squared equals y. Yeah? Since they're both solved for x. So let me find the intersections here. To the right here. Intersections. So I set the 3 minus 1/4 y squared equal to what? Y. How would you solve that if you were you? Well, you are you, right? So how would you solve it? Get the y's together. Do some magic. What type of equation is that? It's a quadratic equation. And normally when we have a quadratic equation, we just try and get everything on one side. And then we either factor or use quadratic formula or something. And I actually don't hate fractions, but I know most of you do. So I'm just going to clear the fractions out by multiplying everything by 4. Okay? And you know what? Yeah, I'll just do 4. So it'll become 12 minus y squared equals 4y. So that's just me multiplying by 4 to get rid of all my fractions. I'm going to move everything to the right side instead of the left side, only because I want that negative y squared to become positive y squared. And that 12 coming over to the right side becomes minus, doesn't it? Ooh, and that factors. That factors. That's y plus 6, y minus 2. So you have two solutions. They are negative 6 and 2. So your y coordinates, the y coordinates where these two graphs intersect are at y equals negative 6 and y equals positive 2. So that's our limits of integration. We want to go from negative 6 to 2. So do you understand now, like this dy is telling us that we're moving our rectangle this way now, and that this tells me where the y is changing from, and that this is the formula, right, that gives you all the areas added up? That's kind of weird, isn't it? Interesting, cool. All right, could you integrate this? Yeah, you just do that. Those would be power rules and plug in numbers, and it should be good. Okay. So, that could be taken the rest of the way. I'm not going to do that. You'll have an opportunity in the homework to practice this some more. Let me see here if there's anything else I want to do on that. Yeah, I mean, I think that's it. Let me summarize quickly what we have, all right, where we are. If you have some function f on top, some function g on the bottom, and you want to find the area between those, you're going to use, in this picture, it would make most sense to use a vertical rectangle here, right? We have, let me put f of x instead, f of x and g of x. These are both functions of x. So we would use a vertical rectangle right here, and then the formula would be integral from a to b of f of x minus g of x dx, right? That would give you that area. So that would be the area. So long as the f is above the g, that's what we would have. All right, now the other possibility we could have would be something like this. I'll do it like that. So are these functions of x? Are they functions of x? Do they pass the vertical line test? No, right? These curves do not pass the vertical line test. Do these pass the vertical line test? Yes, so they are functions of x. These do not, right? But if they don't pass the vertical line test, do they pass the horizontal line test? Yes, so these are both functions of what? Y, right? So the one on the right side I could call f of y, and then the one on the left side I could call g of y. And then what I'm doing is I'm doing a rectangle in here like this, and I'm adding those up. Now, where they hit each other, I'm going to call that C, and I'm going to call this one up here D. So what would the formula be for the area of that region bounded by those? The area would be what? Integral C to D, f of y minus g of y, dy. So as you work through your homework, you're going to be using one of these two formulas. The big indicator for which one to use is is it easy to solve for y? Do your pictures pass the vertical line test? Then you want to use this. If it's easier to solve for x and your functions pass the horizontal line test, or your curves pass the horizontal line test, then you want to use this formula. And there's sometimes where you can use either one. It doesn't matter. It doesn't matter which which ones you use. All right, we still have time. Do y'all want to do another example, or can I move on? Let's move on. Yeah. Move on. Okay. I would like to allow you the time at home to kind of work through some of these problems, see how much you can do without too much more instruction on it. Just work on your graphing, right? Take your time on the graphing. Use your calculator to help aid you in figuring out, what the regions look like. All right, let's talk about 7.2. I at least want to plant the seed here today. Okay, this section is called volumes. Now, there's kind of like two topics in here, but the one that I'm going to start with right now is called volumes of solids of revolution. Volumes of solids of revolution. So everyone knows that solid is, three-dimensional, not two-dimensional. So when we talk about the volume of something, we're talking about the amount of stuff inside of a three-dimensional object, as opposed to the area of something which is on a flat sheet of paper, right? So somehow we're going to be talking about volumes of these solids, and then they're solids of revolution, which means they're all very, very much together, and they all, march in the streets, and it's a revolution.
You were smiling before you even said that.
Did I smile? I thought I kept straight face.
Like when you were revolution, I saw you smile.
It's revolution. No, revolution meaning revolve, like it literally comes from that. So let's take a look at this. I have a little animation for you. There we go. Okay, so this particular animation that I'm showing you comes from the Wolfram website in what they call their Wolfram demonstration projects. And most of the stuff that I show you in this class is code that I've done, but this one I'm not taking credit for. This is someone else's stuff. And it's actually an awesome program that they've written. And they actually have all the code here for it too.
Wait, can you go back real quick? Right in the middle? I'm just curious.
Oh, you mean...
Right there. Yeah.
They have a lot of built-in functions in Mathematica that you just call up the routine. So
C++.
it's C++ based.
Okay.
It's a C++ based language, but it's its own language. Okay, here we go. So do you agree we have two curves, right? Those are both functions of x. And I couldn't get it to take the functions off. I wish these weren't here, but yeah, we've got two curves, right? And then let's say we're going from point A to point B. What we've done so far is we've found a way to calculate that area, right? Okay, that's the formula. That's what you're going to do for homework. But what we're going to do now is we're going to imagine, if we could, that this flat sheet of paper is no longer here, but it's actually living in three-dimensional space. All right? Yes? I mean, that's what it is, right? And then what we're going to do is we're going to imagine, if we could, taking that area, right there between them, and spinning it around the x-axis. Like that. Do y'all see it spinning around the x-axis? All the way until it gets back onto itself up there. And do you see we have a solid? Yes? Yeah, y'all can see that solid? Now, I'm going to take I'm going to make it a little transparent so you can see the inside of it better. Okay, so that's, do you see that we have a hole in there, but it's not like a straight cylinder, it's like curved, right? Because it's the inside of it is actually dictated by the bottom function swinging around. So, what's the volume of that? That's the question, okay? What is the volume of that solid? That seems like it might be tough to do, yes? Would you agree? That seems tough. It's actually not. It's not that hard. As long as we understand how Riemann sums work and how we can come up with formulas for things. So let me take this back. Take this back, swing it back up here. I was going to say something about that. If I change the functions, right? If I change the functions, let me just change the shape of these a little bit. That's kind of boring. Oh, yeah, you know what? I'll make it flat on the outside. There we go. Well, let's do something on the inside of that one. No good. That's changing the height. There we go. There we go. That's more interesting, right? And now let's swing that one around. My computer's trying to keep up. So we have this one now, right? I'll take the... So from the outside, it looks just like, good old, just like you punched a hole in a... But inside, there's some other stuff happening. So let me... So you can see through it now, right? You see how the inside's not completely cylindrical. So what's the volume of that, right? All right, so that's what we want to do. All right, we want to find that we want to take a region between two curves, take that region, we want to wrap it around the x-axis, and we want to figure out what the volume of that is. Later on, we'll wrap it around the y-axis. Because if I wrap that around the y-axis, that's going to give me a completely different geometric shape, isn't it? Yeah, so that'll come later, but I just want to plant the seed as far as what we want to do, all right? So now I'm going to show you how we're going to do it, all right? Check this out. It's not that bad. So let's go back to this picture right here. We have a function here, f, and we have another function down here, g. And I'm just going to put it here. They could hit each other. They don't have to hit each other. And we're going to go from A to B. And we want to wrap it around the x-axis, right? See if you can follow this approach. Dalton, you all right today? You all right? No? I'm afraid you're missing some very fun stuff, right? Yes, everyone can agree. Here we go. About all I know what to do at this point is find the area of that rectangle, right? Yes? And I had you earlier taking that and kind of imagining drawing that rectangle over here on the side, right? This. And we could find the area, and that was no problem. If I asked you to take just that sliver and wrap it around the x-axis, just that sliver around the x-axis, what shape would we have? What would that, in your own words, what would that shape look like if I wrap that around the x-axis? A disc? Circle? Here's my x-axis, right? If I take that top edge and wrap it around, I would have something like that, right? Kind of. But then the inside edge right here would go around also. And wouldn't it make this thing hollow? Wouldn't that hollow it out like this? Right? Does that look like a washer to you? A washer. Okay. So disc, yes, a disc would be solid though, right? No, it wouldn't have a hole in the middle. I'm talking about a washer like for a bolt. You have a bolt, you have a washer, right? Doesn't that look like a washer? Yes? I wonder if we could figure out what the volume of that washer is. Listen to me carefully. If you could find the volume of this single washer, come up with a formula for it, then wouldn't you just have to add up all the washers? Yes? So I wonder if we can just come up with a formula for just the volume of this single sliver of washer. So let's think about this. To do this, first let's lay it sideways so we can maybe work with it a little bit better. So this is my washer laying sideways. My washer has some thickness to it, right? How thick is that washer? How thick is this washer? dx, right? That's a dx. So I know this width right here is dx. And so that right there is dx. Well, it still may be a little bit hard to visualize. So how about we do this? Let's take that same washer and let's not punch the hole in it. And then let's take a look at the smaller washer. That's the inside. Do you all see that there's like the big washer and then it's almost like we took out this smaller washer inside? Now we're back to discs, yes? You have this disc, whatever the volume of this disc is, if we subtracted the volume of this disc, right? So if we subtract this, right, then you get that, yes? Okay. Y'all still with me? All right. So if I could come up with a formula for the volume of that, then I could use an integral to add them all up. What is the formula for the volume of that? Well, it's the formula for the volume of this minus the formula for the volume of this, right? On a side note, what is the volume of a cylinder? So you have to go back and just think pre-cal or somewhere before that. What's the volume of a generic cylinder? It's pi r squared times the height. That's the volume of a cylinder, isn't it? And if you look at the picture, here's your height of your cylinder. And then the radius is from here to here. That's radius, right? So pi r squared, isn't that the area of a circle? So what you're doing to find the volume of a cylinder is you're taking the area of the top surface and you're multiplying it times the depth of the surface, or the solid. That's where that formula comes from. So can we take this on faith that we agree that this is true? All right. So now come over here and realize that these are both just cylinders, right? These are both cylinders. And now comes the fun part. Do we know the height of this cylinder? dx. Do we know the height of this cylinder? dx. Okay, I'm halfway to the formula. I just need to know the radius, right? So what is the radius of this one right here? Well, that's the distance from here to here, right? But that's the distance from here to here. But that's the distance from here to here, right? Yeah. Which is f, right? That's f. And then what about this guy's little radius? What's this little guy right here? What's its radius? Well, that's this little radius, and that's that little radius, but that came from swinging this guy around, but that's just g, isn't it? So this radius here is g. Yeah? You following me? Yeah? It's creepy? Oh, crazy. Okay. All right. Yeah. So tell me what the volume of this disk is. According to the formula over there, the volume of this disk is pi, right, times its radius, which is the f function. I'm going to put it in brackets. F of x, right, radius squared. Yes? Times the height, dx. Crap, that is a formula for the volume of that piece. Now, what is the formula for the volume of this piece? Pi, but the radius this time is g of x squared and then times its height, which is dx. So if we want the volume of this one, we do this minus this, right? So let me write that down. The volume of this one would be pi times its radius squared times dx minus this one, pi times its radius squared times dx. And as bad as that formula looks, they both have pi in them, right? So I could pull that out. And they both have dx in them, which I could pull out, couldn't I? Yeah. Now watch the way I write it. I guess I can do it right now. Is it all right if I just already jump to the idea that I'm going to add all these up? There's an infinite number of them. So I'm going to use an integral, right? So I'm going to do an integral and add them up. Now pi is in both of them, and pi is a constant, and that can come out of the integral. So the pi is out here, right? And then they both had dx, right? I can't pull dx out because dx is not a constant. But I can kind of pop the dx to the back, can't I? Now that means inside here I have whatever was still left, which is what? F of x squared minus g of x squared. F of x squared minus g of x squared. And that is the volume of the solid generated by rotating the region bounded between f and g. Oh, I'm missing my limits of integration. A to b, sorry, A to b. This is the volume of the solid that you get when you take this region that's bounded by f and g between a and b and rotate it about the x-axis. Look at what this integral is saying. I mean, this is not that bad. Because if you have two functions, all you have to do is square each of them and then subtract them. And then do the integral and just multiply by pi, and that's the volume. The most important part of this is how I came up with the formula, not memorizing the formula. Because as we continue it, as I said, it's just going to we're going to keep on having to come up with formulas. And this is what I'm going to be testing you on during, the exam. I want to see you coming up with this part of it, like putting it all together. All right, well, I think that's enough for today. We'll come back and we'll start doing more. Oh, and think about this. If we wrap it around this axis, right? Right? We might have to turn our rectangle sideways. And then all that happens is we go C to D, f of y, g of y, dy, right? I mean, everything's going to be just like the area was. All right, have a good weekend. Work on your 7.1. Try and have a little fun today, or this weekend, maybe. Let me turn off my camera real quick.
All right, no problem.